So, hi friends, a very good evening. Let me please check if everything is working as expected before we jump into the discussion itself. Just give me a couple of minutes. I'll just check the quality of stream, the audio, etc. You should be able to see my screen now. So, please confirm in the chat window if you're able to see my screen and hear to my audio. Right. So, can you please confirm? Is there any glitch with audio? I can just let me check. Can you hear me, folks? Yeah, I can hear myself, so no glitches whatsoever there. So if you can hear and see me, if you can hear me and see my screen, that's a good start. We'll start the session at sharp 7 p.m. right? So I'm just waiting for everyone to join in. Again, we have a bunch of questions today that we'll solve one by one. Okay, everything is fine. Good. So no glitches whatsoever. Good. That's good to know. So let's just wait for a minute or so. We'll start the session at 7 sharp. Thank you for joining in, everyone. Thank you, folks. Okay. I have all the questions in a doc. I'll just share that right after this. Okay, good. So I hope everyone revised the topics that we mentioned earlier. So somebody is asking a good question. Do we need to make our own notes? And are the notes sufficient to get a rank 100? Again, to get rank 100, what you need is practice and problem solving ability and conceptual clarity, not just notes. This is notes that we prepared for the benefit of our students. Some students prefer to make their own notes, and for them, we recommend them to write their own notes because there is nothing better than writing your own notes in the words that you understand best. Some people even write in their mother tongue. Like we know some students who write notes in Hindi, Telugu, Tamil, etc. So that's for them. So somebody is asking what are the topics. We've already announced that in the announcement video. So we'll cover those discussions themselves. Again, we'll start subject by subject and we'll cover almost all the subjects over the next few months. We are starting with data structures and algorithms first. We'll cover every subject including computer organization. But we want to go one subject after other. We are starting with data structures algorithms because most students are comfortable with that subject, right? It's already 7:01. Let's get started. Here is our first question. Please take a minute or so to answer it. Okay, I have a timer also today, so please take some time. Let's take 90 seconds to finish this. 1 minute, 30 seconds. This is the first question of the day. Simple question, fairly easy. Okay, I'm looking at the chat window to see students' answers. So again, don't be in a hurry, take your time. Getting it correct is more important than speed. Okay, I see a few answers here and there. Let's take 30 more seconds because students are still figuring it out. So 2 minutes, let's spend 30 more seconds on this. I see a few answers here. Okay, we also have our team joining in for the discussion who are responding to some students' questions. Cool. Okay, it's almost 2 minutes up. So let's stop the timer and let's get into the solution. Again, this is an easy problem. Okay, so we are starting with some easier problems, then we'll go to more complex, some hard problems, most of them medium problems. So this is our pre-order traversal. What is pre-order traversal? Pre-order traversal is first you have root, then you have left, and then right. That's your pre-order traversal. This is your in-order traversal. What is in-order traversal? Left, right, root, right? So now what is the question here? What is the right child of the root node? We can easily obtain the root node here, right? So because all the nodes are A, B, C, D, F, G, H, I, J, all of them are unique values. Because this is the pre-order, G has to be the root. That is straightforward, right? That's cool. Now what is the question here? What is the right child of the root node? So here you have your right subtree and you have your left subtree, right? So after you have root, somewhere here is your, look at this. So somewhere in this region, your left subtree ends and your right subtree begins, right? So sorry, this is in order, right? So this is not post order, this is in order, I'm sorry. So in order is left, root, right, I'm sorry. Okay, so this is your in order, this is your pre-order. So if this is your in order, we know what the root is. So G is the root, which means all these elements will form the left subtree. So the left subtree will contain E, H, B, I, C. These 5 will be in the left subtree. J, A, look at this, J, A, F and D will be in the right subtree. Simple, right? Now within the right subtree, which means now if you look at this, we know we can easily separate where the left subtree elements end and where the right subtree elements start here. That should be easy because the right subtree can only have J, A, F, D, which means this is where your right subtree is, this is where your left subtree is. Because we have two orders, right? We have pre-order and in order. We don't have just one order, right? So which means now look at this. This is our right subtree. Now this right subtree is recursively listed again in pre-order, which means the root has to be D here. Again, look at this. This is our right subtree, right? In the pre-order, our right subtree is having a root of D. So which means here this right subtree will have a root of D. And what is the question? What is the right child of the root node? The right child of the root node is nothing but the root of the right subtree, which is nothing but D. So answer here is D. That's it. Very simple. If you know what is pre-order traversal, if you know what is in-order traversal, again, whenever there is a problem on pre-order or in-order traversals, because so as not to get confused, I always write this format. Again, in the course videos also, we explain how to, we have solved lots of similar problems in the course videos as solved problems, practice problems, etc. It's a very simple, easy problem. Typically a 1 mark problem in GATE, right? So simple to crack, easy to finish. Okay. Shall we go to the next question now? Okay, simple. Some of you who have answered J, think where you have gone wrong. It's very easy to make a silly mistake. I think some of you have answered J because you thought that this is the right subtree. Again, very often made mistake, right? From the in order, you know that this is your right subtree. Then you think that J is the root of the, look at this, you got confused. Some of you have answered J primarily because you got confused between in-order traversal and pre-order traversal. To get the root element is always the first element in the pre-order traversal, not in the in-order traversal. So you got till here, you figured out that these elements are the elements of the right subtree. But then you answered J while it should have been D. It's a silly mistake. Maybe there is a small conceptual gap for some of you, but it's a silly mistake which you can avoid. Okay, cool. Sounds good. Okay, let's go to the next question now. Okay. Let's take 2.5 minutes for this. It's again not a very hard question. Please read the question carefully. This is a slightly tricky question where you can do a lot of silly mistakes. So read the question carefully, please. Okay, some of you are putting your answers. Please double check because it's very easy to do silly mistakes here. Okay. Okay, I see a lot of answers already being put out in the chat window. That's good to see. Anyway, since most of you got the answer, no point extending the time further. Let's just, for those of you who couldn't get it, let's just go through and read the question here, right? Again, it's a simple question, slightly lengthy to read and easy to get confused. A stack is used to shuffle a sequence of characters. The sequence of characters are inserted or pushed onto a stack without changing the original order. You can only push in the original order. But any character may be popped at any time and printed. You can print. So to print, you have to pop and then print. Which of the following sequences cannot be printed if the original sequence of characters are GATE? Okay, let's go step by step. Okay, so I'll use this symbol to push, just this symbol to pop. Okay, just to show you. Okay, so this downward arrow basically means push, upward arrow basically means pop. Okay, this is going into the stack, this is going out of the stack. Simple logic. So to print this, how can we do this? Look at this. If we just push G, look at this, push G, push A, push T, push E, you pushed all of them. Now let's pop. So if you pop, you'll get E, so you print E. You pop, you get T, you print T, pop A, pop G. So this can be printed. The question here, which of the following sequences cannot be printed? So this cannot be the answer. Okay. Next, can we print GAAT itself? Let's see how to do it, right? Very simple. You first push G and then pop G, right? Print G. Cool. Then again push A, pop, push A, pop, push A, pop, right? And print. When you pop, you can print, right? Anything can be popped anytime and printed. So you get A. Similarly, push T, pop T, push E, pop. You'll get gate. So this can also be printed easily. Now what about the third option now, right? So let's look at TGAE. Can we do this? Okay. So let's assume we have to go in this order, right? GATE. So we want to first print T, which means you have to push A, you have to push G, you have to push G and A. Then only I get T. So to print T, what do I do? Okay, you push T and you pop T. So you printed T. Cool. Right, you printed T. So this is no more in the stack. The stack now contains G and A. Now you want to print G. You can't print G. Because if you want to print G, first you have to pop A and print it. So this order is messed up. So this order cannot be printed. You can also easily verify that. You can also print TAGE. This is also easy. Right? This is nothing but, look at this. You push G. So this is also not the answer because you push G, you push A, you push T. And then you pop T, print it, pop A, print it, pop G, print it, push E, and then pop E and print it. So this can also be printed and hence this cannot be an answer, right? Again, this can be done. I'm explaining much more slowly so that everybody understands it. If you're solving this problem, you can. Oh, this is a very good question. Okay, so let me start the timer, 2.5 minutes. This is a very good question. So let's use 2.5 minutes for this question. Intentionally, we did not give options here because we want you to work it out. Please think very carefully. It's a very good question. It's my favorite question today, actually. Some of you have started putting in your answers. Please think very, very carefully, because it's very, very easy to make silly mistakes here. I see a few varied answers. None of them are correct, so please rework them. Instead of 2.5 minutes, let's take 3 minutes, because this is slightly tricky and good question. Let's take 3 minutes, that's okay. Let's take 3 minutes. I don't think I've seen a correct answer till now in the chat window. Okay, 3 minutes up. I don't see any correct answer yet. That's okay. That's okay. We'll understand it. To be fair with you, this is by gate standards. This would be considered as a hard problem by gate standard, right? Personally, I think it's a good problem, not very hard if you know how Max-heap works, right? If you look at CLRS problems, exercise problems, you do see some problems like this. Actually, this problem is a modification on a problem that was asked for ISI Kolkata, right? So this is a slightly modified problem. So there is a very similar problem asked for ISI Kolkata. We modified that problem slightly. Okay, very good problem. Okay, okay, people want time. Okay, cool. So let's take 1 more minute then. That's okay. Some of you are working it out. Okay, take 1 more minute. That's okay. Think through it. I don't see. Okay, at least all the chat window answers that I've seen, I have not seen even a single correct answer. I don't think I've seen a single correct answer. It's a Max-heap. I haven't yet seen a correct answer till now. Okay, so 1 minute up. So let me explain it anyway. I think some of you are confused or stuck. Let me explain it step by step. So consider a Max-heap of 1000 distinct integers. Remember, my array starts from 1 to 1000. That's what our array is. Our array is not 0 indexed. It's starting from 1 to 1000. And the 1000 numbers are distinct. The second minimum element in A is the element that is less than all the integers except the minimum element, because all numbers are distinct. This is the second minimum element. Okay. Find the possible array indices of A for which the second minimum can occur. First of all, you have to understand that it's a Max-heap. All the elements are distinct. We care about the position of the second minimum element. The array is from 1 to 1000, and we are storing the Max-heap as an array, not using linked lists and pointers. Right? These are a bunch of stuff. Now, given these facts, right, first thing you have to recognize is, where is the second minimum element? In a Max-heap, the parent will always be greater, because all elements are distinct. Remember, all elements are distinct, right? All the 1000 elements are distinct. The parent will be greater than both the children. Every parent node, for any node, For any node, the parent node is greater than both the children. That's a property of the max heap, right? I mean, that's what you do when you heapify in max heap. Okay, cool. So you have this property, very good. Now, where does the second minimum element occur? Now let's think of a binary heap like this, binary max heap. It could be like this. Again, there are multiple possibilities. A binary heap could also be like this, right? I'm just drawing a couple of variations of binary heaps, binary max heaps. Now this element is greater than both these elements. This element is greater than both these elements. This element is greater than both these elements, which means where can the minimum element be? Look at this. The most important thing is the minimum element will always be, it has to be a leaf node, right? The minimum element has to be a leaf node because it's a max heap. The minimum element always has to be in the leaf nodes. Now, what about the second minimum element? Okay, if the question was just about minimum element, it would have become a medium problem at gate level. The reason this is a hard problem at gate level, again, personally, I don't consider it hard, but by gate standards, this is considered hard. Okay, when I say hard, I only mean by gate standards. The second minimum element, where can it be? The second minimum element can be a leaf node, obviously, right? If this is the minimum element, the second minimum element could be any of the other leaf nodes also. It could be a leaf node, or it could be a parent of a leaf node. It could be a parent of the leaf node. This is the important first step. This is the first important conclusion that you have to arrive at. That the second minimum element, look at this. Imagine if this is our minimum element. Okay, the second minimum element could be anywhere here, right? So for example, imagine this is my minimum element. The second minimum element could have been the parent of this minimum element also, right? Maybe the second minimum element is here, or the second minimum element could have been anywhere here, right? So the first important conclusion that we have to arrive at is that the second minimum element could be a leaf node or the parent of a leaf node. Now, what are the indices of leaf nodes? So the second step in this problem is, okay, given a heap like this, what are the indices? Again, remember the indices start from 1. Okay, so if this is 1, 2, this is how we store a binary tree, right, in arrays, right? 1, 2, 3, 4, 5, 6, 7. These are the indices that I'm writing. Or you store 1, 2, 3, 4, 5, 6, 7, 8. So the leaf nodes, the leaf node indices, when you store a binary max heap into an array, the leaf node indices, as you can see, look at this. 7 is my n. Let's say n is my maximum element, or n is the number of elements that we have here. Let's assume, let's solve this problem for the general case, right? And then we can solve it when n equals to 1000, right? If there are n elements in our binary max heap, then the leaf nodes, what are the indices of leaf nodes? They are from n by 2 plus 1 to n by 2. Sorry, to n, sorry, my bad. Look at this. The indices of the leaf nodes will be n by 2 floor plus 1 to n. Because n here equals to 7. Look at this. What is n by 2? N by 2 is 3. Floor of n by 2 is 3. 3 plus 1 is 4. So the leaf nodes will be in indices 4, 5, 6, 7. Or in other words, if n equals to 8, this even works here. Again, you can work out this problem by just using these two examples. You can also theoretically and rigorously prove it, but that's not our objective here, right? Our objective is to arrive at a solution. If you have n elements that you're storing in your max heap, then the leaf nodes could be anywhere from n by 2 plus 1, floor of n by 2 obviously, to n. Like here, n equals to 8. So the leaf nodes are, what is n by 2? 4, 4 plus 1. So 5, 6, 7, 8 are your leaf nodes. So your second minimum element can be anywhere from n by 2 plus 1 to n indices. Okay, n by 2 plus 1 up to n. The index number could be anything. Or what about the parents of leaf nodes now? Look at both these examples. What about the parents? See, the leaf nodes can be there in the indices in your array from n by 2 plus 1 to n. What about parents of leaf nodes now? Look at this. What are parents of leaf nodes? These are your parents of leaf nodes. What are parents of leaf nodes here? This is a parent of a leaf node. These are your parents of leaf node. Again, it's very simple to arrive at the fact that the parents of leaf nodes will be in the range of n by 4 plus 1 to n by 2. Right? Again, remember, a max heap is a binary tree. which is full except at the last level, right? Every other level it will be full. So that's why the parent of the leaf nodes will be in this range, which means your second minimum element can be anywhere from n by 4 plus 1, floor of n by 4 plus 1 up to n, because this is the range of indices in which parents of leaf nodes can be there. This is the range of indices in which leaf nodes can be there. And your second minimum element could be there as a leaf node or as a parent of a leaf node, which means your second minimum element could be there anywhere from n by 4 plus 1 to n. Here what is our n? Our n is 1000, which means from 251 to 1000. That's it. It's a very, very good problem. Okay, it's a tricky problem because there are two leaps that you have to make. The first leap is to figure out that the second minimum element can be a leaf node or the parent of a leaf node. That's the first logical thing that you have to arrive at. Second logical thing you have to arrive at, which is actually simpler, is what is the range of indices where leaf nodes can be present and parents of leaf nodes can be present. That's the easier second part. Okay, it's a very good question actually. Okay, sounds good, sounds good. Okay, cool. Let's go to the next problem. Okay, it's again, if you could not solve it, that's perfectly okay. Okay, this is considered a hard problem by GATE standards. Okay, in an actual GATE exam, you will not be able to solve every problem. If you think the problem is too hard, you can skip it, number one, and not have the penalty of negative marks, or over the next few months, your problem solving skills will improve and you will be able to tackle problems like this. The reason we gave one or two slightly harder problems is so that you're exposed to what a hard problem might look like in GATE. Okay, again, in the last 4 to 5 years of GATE papers, we do not see hard questions. Okay, GATE questions nowadays are on the medium or easy end if you look at the last 20 years of GATE question papers, but they're tricky, very easy to make silly mistakes. Okay, let's go to the next question, guys. Okay, let's look at this simple straightforward question. Let's take 90 seconds for this, 1.5 minutes. Simple question. Some of you have already started answering, so let's see. Somebody says GATE 2020 was hard. You have not seen what a GATE hard paper is. 2020 is by no means a hard paper. It was harder than the last few years, but not at all hard by last 20-year GATE question papers. Okay, a lot of people are putting in the answers. Okay, let me read the question. Okay. Somebody says D. Okay, I think it's just a fake ID because I don't see a genuine name there. Okay, so time's up. So let's go and look at this problem, right? Again, this is a very easy problem by GATE standards, right? Typically a 1-mark problem. Which of the following is not a constant time operation? Which of them is not order of 1, right? Obviously, if you just read these options, dequeuing an element from a circular queue, again, that's simple, right? You have a circular queue like this, right? This is your circular queue. You have this back pointer, you have this forward pointer, right? And this is your front, this is your front of the queue, this is your rear of the queue. Again, because your pointers in both directions, right? And it's a circular queue. If you want to remove something, if you want to dequeue something from the front, right, from the front of the queue, you can adjust all the pointers by just adjusting, because you have all the pointers and it's a circular nature queue, right? So you can actually, it's very simple to see that you can adjust the pointers in order of 1 time, right? Pushing an element into a linked list based stack, obviously to the front of the linked list or to the front of the linked list, you just add, right? That's also an order of 1 operation. So this is certainly, so this is not order of, so this is order of 1. So this is surely order of 1. This is also order of 1. Insert an element into a min heap. Again, we know that this is order of log n, right? Very simple, because when you insert an element to the heap property may be lost. So you'll have to again heapify, and heapify itself could take order of log n time. Very simple question. So C is the right answer. Trivially easy to get through, right? Cool. So let's go to the next problem now. Okay. This is also a good question. This is a good question. Please read it carefully. This is a good question. Again, please read it very carefully. I think some of you are confused. What is level order traversal? Imagine if you have a binary search tree like this, right? A level order traversal is first you do this level, then you do this level, then you print elements in this level. So level by level, left to right. That's what a level order traversal is. Oh, I forgot to start the timer. My bad. That's okay. Let's take, some of you have already started answering the questions. So let's see. I see all options A, B, C, D all over the place. Okay. Which means some of you are wrong, some of you are right. Oh, it's all over the place. Okay. So those of you who don't know what is level order, I hope you are clear enough. Somebody says, do the numbers have the original meaning? Yes. By numbers, they have an ordered. You can compare any two numbers. Okay, I see all options A, B, C, D all over the place. Okay. So take 30 more seconds, and at 1.5 minutes in the timer, I'll stop it and we'll go to the explanation. This is a good question. Not hard, but good. Again, somebody says you need post order plus in order. Guys, this is not a textbook question, okay? Everybody knows that you need that in a general BST. Please read the question carefully. If the question was that straightforward, why would it be asked? When I said it's a good question, there must be something tricky in here. Otherwise, it would have been a trivial question, right? Okay, I see almost all the possibilities here. By identified, it means that you can actually draw the tree itself. You can draw the binary search tree uniquely. Okay, sounds good. So, okay. I see all the answers here, so it's better we discuss the solution thoroughly, okay? The most important thing in this is you have a binary search tree of unique numbers. This is very, very important. All numbers are unique. No number is repeated. That's a very important property that you have to read carefully. That's why I said you have to read carefully. Which of the following statements is true? Statement 1, it can be identified or reconstructed. Somebody said, what is identified? We can reconstruct the binary search tree using post order traversal alone. Now, what is post order traversal? You have left, right, and then root, right? So if you are given, again, remember that all the numbers are unique. Okay. So by just looking at the post order, we can obtain the root. So let's try to reconstruct the tree, right? So we got the root because we know the last number will be the root. Okay. Now, remember it's a binary search tree, which means the left subtree will contain all the numbers which are less than the root, because all numbers are unique here. There are no repetitions. This is a very important aspect here, because all the numbers are unique. The left will contain, the left subtree will contain all the numbers that are less than this. The right subtree will contain all the numbers that are greater than this. See, in a typical situation, we can, given a post order traversal, we can find what the root is very easily. The biggest challenge is how do you break down the left and right? That is often the big challenge. In this case, we can break because all numbers are unique and we have the root. We just simply parse these values, which again, we'll get basically a series of numbers, right? We will just parse these values. Wherever you encounter numbers that are greater than the root, everything here, these will belong to the right subtree. These will belong to the left subtree, right? Very simple. Now, you can again construct this left subtree recursively, the right subtree recursively, same logic. Now, you have the pre-order of the left subtree, you have the post order of the left subtree and right subtree. You can find what is the root of the left subtree by looking at the last element. You can place it here and so on and so forth. Recursively, you can build it. So statement 1 is obviously true. What about statement 2? That is a more interesting thing actually here. Statement 1 is easy to figure out. Okay, statement 2 is where it gets much more interesting. That it can be reconstructed using the level order traversal alone. So what is a level order traversal? Imagine if you have a binary search tree like this, right? See, look at this. Can you determine where each level ends? Again, this need not be a complete tree. Okay, it just has to be a binary search tree. That's it. It just has to be a binary search tree. That's it. Right? Again, given a level order traversal, you know that the first you have all the elements in level 1, all the elements in level 2, all the elements in level 3, and so on and so forth. All the elements in level 1 you can easily obtain because level 1 only has root. So take the first element in your level order traversal, that will become your root. So you got the root, right? Very simple. Okay. Now what about the left and right? Look at this. This is very interesting. Now you have level 2 elements. Okay. So let's actually put in some numbers, right? So that it becomes easy. This is a binary search tree, right? So let's assume there is 10 here. Let's just take an example. Let's assume there is 10 here. Okay. So we have level order traversal. 10 will always be in the first because this is the first level. Second level, you have a bunch of numbers. You should be able to determine, look at this, the second level may have only one node or it could have both the nodes. It may not have the left node, it could have the right node. You don't know which of them exists because this is just a binary search tree. You could have a binary search tree like this. This is also a valid binary search tree. This is also a valid binary search tree, right? So now look at this. The moment we got the root node, we go to level 2 elements. Now, when we go to level 2 elements, can we determine whether this element exists or not? Remember that all the elements are unique. In level 2, there can only be 2 numbers at most, no more than that. Simple. So this, if you have a number that is less than the root, then that has to belong here. So you got this also. If there is a number followed by this, which is greater than this, then you got this number also. So given, see, you can determine where the level 2 ends because level 2 can have at most 2 values, right? At most. And if you have a number which is less than the root, you know that this, here you fill this, right? Otherwise you fill this. Now you got this number also and this number also. Now same thing at level 3. At level 3, what you do is, you know, look at this, all these numbers now. So at level 3, the tricky part is this. How do you now determine, this? These elements, this element, if it exists, is going to be less than this element also. Okay, level 3, you don't know whether this exists or not. Again, first draw a full tree. Draw a complete binary search tree. Now, for every node, ask this question. Okay. Does this node exist or not in the structure? So this is easy to figure out. Root has to be there. You can figure out whether this exists or this exists from the sequence. Now, whether this node exists or not, how do you determine that? Now, after you finish level 1 and level 2, if the next number that you see is less than the root node of root node of this, suppose the next value that I encounter, let's assume, is less than, because this I know, this we know, this we know. So the next value that you encounter in this sequence, if it is less than this, it has to be here. It can't be anywhere else, right? If the number that you encounter is greater than this, right, but less than this, then it has to be this value. If the number that you encounter is greater than this, it is greater than this, and it's also less than this, then you know it has to fall in this place. So there is a unique if-else condition for each of these nodes. There is a unique if-else condition that you can check and fill these nodes. See, this node basically means that it is less than this node value. This basically means that it is greater than this but less than this. This node, whether it's present, so given any value that you encounter in your level order, you basically try to see where it fits into your complete binary search tree. And that's how you start filling it level by level, step by step. All this is possible only because there are unique numbers here. So statement 2 is also correct. Again, statement 2 is a tricky part. Statement 1 is actually easy. Okay, I think a lot of people are confused between A and B, because A says both statements are true. Statement 1 is true, that is trivial. It is statement 2's truth or falsity which is tricky. Okay, this statement is the tricky part to figure out. So A is the right option here. Both statements are true. Again, the way you figure out, given a level order traversal, the way you fill it in this tree is you go node by node and see the values that you encounter, where do they fit in. If they don't fit in here, this whole subtree does not exist. If it fits in here, there could be a possible subtree below that. So you go start filling each of these values that you encounter, each of the values that you encounter in the level order, try to place it in the appropriate cell or appropriate position, because for every position there is a concrete logic, there is a concrete if-else condition. For example, for this has to be greater than this but less than this, right? That's the tricky part here. Again, figuring this out is the tricky part. That's why I said this is a good and tricky question. Figuring out statement 1 is trivial. Okay, slightly tricky, but a good question nonetheless. Okay, cool. Sounds good. So let's go to the 6th question now. Okay, it's already 7:40, but that's okay. Okay, this is a simple question. Let's solve this. This is an easy question by its standards. So let's take a minute and a half. Should be easy to solve. Again, if the numbers are not unique in the previous example, we can't solve it, but that's the key here. So for the previous question, if the numbers are not unique, it won't work. Okay, so anyway, our team is also answering a few questions in the comments chat section. Okay, I see a few answers. Okay, let's take 15 more seconds because not everybody has answered. I see a bunch of answers here. Again, this is simple, straightforward question. Okay, sounds good. So a quick, some of you are asking this question. In the previous question, if the numbers are not unique, then things won't work. You can't uniquely identify just using post order or level order traversal. That's the key here. Okay. So coming back to this question now, okay, so it's very simple, right? So you have 7, 2, 3, 4. So your stack will contain 7, 2, 3, 4. You pop it, multiplication, which means 7 and 4, 4 and 3 will be popped. You will perform multiplication. So you would get 12. So your stack top is 12, 2, 7. Then you have an operand star. So the first two things will be popped and then this will be performed. So 12 into 2 is 24. So you pop both of them, you get 24. Then you have plus. So plus is an operator. So 24 plus 7 is 31. So your stack only contains 31 now. Then, okay, so this is also done. This is also done. Then you get 9. So you push 9, right? Then you have minus, right? So the moment you get minus, you have to perform subtraction. Okay, again, some of you might do 9 minus 31. What you should do is 31 minus 9. Okay, that's a very confusing thing. Look at this. If you have 2 minus, sorry, if you have 31 minus 9, what would the postfix expression be? This is postfix, right? 31, 9 minus, right? This is what the postfix expression would be. So you get, so when you push it, you get 31. Then on the stack you have 9, then you get minus. So whatever you get, 31 minus 9. So please don't do this. This is the silly mistake that some people commit. So 31 minus 9 is 22, right? 22, yes. So this is done. So this is done. Then you have 2. So push 2 into the stack, push 7 into the stack. Then you have exponent. This is your exponent, right? So 2 and 7. So it's not 7 square, it is 2 power 7. Look at this. If you have 2 power 7, how would the stack look like? What will the postfix looks like? 2, 7, this. So how would it look in the stack? In the stack, it will look like 2, 7, and then this. So 7 and 2 does not mean 7 power 2. This is a common mistake. It means 2 power 7. What is 2 power 7? 2 power 7 is 128. You push 128 into the stack. And then finally, this is done, this is done. You have plus 128 plus 22. What would you get here? You get 150, which you push into the stack. You reach the end of the expression. So you print 150. So the answer here is 150. The only silly mistakes that people fall for is the order of operands that people mess up. Instead of 2 power 7, some people might do 7 square. Instead of 31 minus 9, they might do 9 minus 31. That's a common mistake that people make. Okay, very simple point here. Okay, cool. Okay, easy question, 1 mark question. Okay, let's look at this. Okay, let me just make it full screen. View full screen. Okay, sorry. Okay, slightly lengthy question to read, but a good question. So let's take 2.5 minutes for this. Okay. Oh, somebody has a good question. Okay. Yeah, not related to this problem. I'm looking at, again, anything that you think is incorrect in our explanation or anything that is not fully clarified, because we want to finish these live sessions in 1 hour. Hence, I may not be able to answer every case that students bring up in the chat session. So anything that we cannot answer, as some of our teammates are mentioning, please shoot an email. We'll try to answer as quickly as possible. Okay, I see a few people answering. Yeah, this is time taking. That's okay. Just use a calculator on your phone or computer. Let's take some time here. That's okay. This could be slightly time taking. Let's take 3 minutes. Okay, 30 more seconds. Okay, we see a few answers. This is easy but time taking. Okay, so a quick note is in the interest of time, because we want to finish these questions in 60 minutes. Again, that's why we started sharp at 7 p.m. without any delays, right? Because there are a lot of students who join exactly for the 60 minutes. So we may not be able to answer every follow-up question that students ask in the chat window. So anything that you're not convinced with or you think there is a problem somewhere, please email us at gatecsc@appliedcourse.com, right? So gatecsc@appliedcourse.com. Anything that you're not convinced with, again, please think through the explanation that we have given. Try to convince yourself that it is correct. If you strongly feel that it is incorrect, again, you can watch this video on YouTube right after this for a while. Again, most importantly, if you're not fully convinced or if you think there is an error somewhere in our explanation or in our arguments, please shoot an email here. We will try to respond back as soon as we can, right? Of course, if you get too many emails, it will take us a little time to respond to everything, right? Again, we want to finish this in 60 minutes in the interest of everyone's time. Okay, so okay, let's go here. Okay, this question here is, okay, what are we doing here? A hash table of length 12, okay, and the hash function is modulo 12 with linear probing. Cool, right? So you've already, after inserting 6 values into the empty hash table, we got the following hash table. Which of the following order of insertions could result in a table? Now, if you notice, first thing that you have to notice here is the numbers are more or less the same. Okay, for 1995, if you do modulo 12 using your calculator, you will get 3. For 1997, you will get 5. For 2020, you will get 4. Again, I've pre-computed this. I don't know this by heart. I've used my calculator and pre-computed them. So here you get 3, 8, 5 and 5. This is what the k mod 12 will result in. Okay. So now if this is the sequence in which we see these numbers, right? Look at this. If this is the sequence in which we see these numbers, what is the question? Which of the following order of insertion could result in the above table? Okay, let's see. Let's see if option A is the right option. First we insert 1995. It will get hashed here. The whole hash table is empty. So it is here. Cool. Then we get 1997. 1997 would get hashed to 5. So this is also cool. No problem. No inconsistencies. 2020 will get hashed to 4. Till now everything looks good. Next 1947, which will get hashed to 3, right? But I go to 3, 3 is full. I do linear probing. So we go to 4, 4 is also full. We go to 5, 5 is also full. So we place it in 6, okay? Till here everything is cool, okay? So this will be placed in 6th location, cool. Next 2012, okay? Now what happens to 2012 now? 2012 will get hashed to the 8th location. 8th location, only these 4 locations are full at this point of time. These locations are empty. So 2012 should get stored in the 8th location. But here we have 2021, which means option A cannot be the option, right? Obviously option A cannot be the option, right? That's important, okay? Now can option B be the right option? 1997, 95, 2020, okay? So let's again, just, you can solve this faster if you're comfortable, but I want to explain it clearly. So 97 is 3. 97 would get hashed to 5, I'm sorry. So we go to 5, 95 would get hashed to 3, so 3, perfectly all right. 2020 will get hashed to 4, so we go to 4. 1947 would get hashed to 3, but 3, 4, 5 are full, so we'll go here. Then we get 2009. 2009 would get hashed to 5, right? We hash it to 5, but 5 is full, linear probing, so 6 is full, so we place it here. 2009 also went into the right location. Next comes 2012. 2012 will get hashed to position 8. So this 2012 would have been present here, but here we have 2021, which means this can't be the answer. Now, if you look at option C here, look at this. All these things will behave just like in the previous case. Okay, till here everything will behave the same. Now comes the fun part. Okay, you have 2021. So 2021 will get hashed to 5th position. The moment we go to 5th position is full. Linear probing, 6th position. 7th position is also full. So we'll place it in the 8th position. Cool. Simple linear probing. If you know the modulo of each of these numbers with respect to 12, and if you know what is linear probing, okay, so this is in the right position. Now 2012. 2012 will get hashed to 8th position, but 8th position is full. So we'll place it with linear probing in the 9th position. So option C, if the sequence of numbers that we see is this, with k mod 12 as our hash function with linear probing, we can see this sort of index and key values in the hash table. So option C is the right option here. Again, this is not a hard problem. Again, because this is just applying the hash function and the linear probing concept, but this is slightly time taking. Okay. Again, there are easier ways to solve it faster, but I wanted to explain the cleanest way without any confusion. Okay. Very simple. It's C. That's it. That's all the answer is. Okay. So let's go to the 8th question now. This is also a good question. Not hard. It's a good question. Let's take about 2 minutes for this. Again, please avoid silly mistakes in this problem. This problem is fully prone with silly mistakes. Please avoid silly mistakes. This is an easy problem, but silly mistakes makes it actually medium. Again, please read the question very, very carefully. Okay, I don't see any answer, so let's extend the time to 2.5 minutes. I don't see any answers in the chat window. I hope the chat window is working. Oh, okay, I have to scroll down. Okay, cool. I see very few answers, so let's spend some more time here. Let's make it 2.5 minutes. Again, in the early stages of your preparation, getting the answer correct is more important than speed. Speed you will build over time. I expected the silly mistakes that students are making. Some of you got it right, but a lot of you are making silly mistakes. There is one silly mistake that I made when I was solving this problem and my teammate corrected me. I see some of you making that mistake. Good, good, good. Oh, it's already 3 minutes. I'm sorry. I was looking at the comment section and I forgot about it. Okay, so this is, again, we have a question in our solved problems in the course videos when we learn what is a triangular matrix, etc. We have a problem from old gate question, 1994 gate question, right? So this is basically a modification of that question, making it slightly tricky and prone to errors. Okay, we have a solved problem in the course videos where we explain something very similar for, I think, lower triangular or upper triangular matrices. I don't remember the exact question, but this is based on the same question, but making it much more tricky and easy to make silly mistakes on. Okay, so let's see. We have a lower triangular matrix of size 99 cross 99, which is stored in a one-dimensional array optimally. This is important. We want to store the lower triangular matrix as optimally as possible. Okay, what would be the index of element A2423 in the array? Assume that the array index starts with 0, but the matrix indexing starts with 1, 1 and row major ordering. Look at this. The confusing part here is the array indexing starts with 0, but the matrix indexing starts with 1, 1. First row, first column type of stuff, right? So if you notice, okay, look at this. This is our whole matrix. It's a lower triangular matrix, which means all the upper triangular elements will be 0. Okay, the first element is 1, 1 and the whole size is 99, 99. Right? It's a matrix of size 99 cross 99. Okay, so just be careful that the index for this array A starts from 1, 1, goes to 99, 99. All these elements, upper triangular elements, at 0. So if you want to store this as an array, we only store the lower triangular elements because we know upper triangular elements are always 0. So we want to store it optimally. Let's not forget that. So when we store it in a lower triangular matrix, when we convert this into an array, look at this. First we want to convert it. So here there will only be one cell. In the second row there will be 2 cells. In the third row there will be 3 cells. Fourth row, so on and so forth. So what do we want now? What is the index of A2423? Which means 24th row, my bad. 24th row, 23rd column, right? Remember that first we will store first row, second row, third row up to 23rd row. First row contains only one element. Second row contains only 2 elements because we don't store the upper triangular elements because we know that they are 0. Okay, so you can just completely avoid storing it. Okay, because we want to store it in a one-dimensional array optimally. This is important. Okay, the third row will have 3 elements, so on and so forth. The 23rd row will have 23 elements. So when we store it into a linear array, first we will store the first 23 rows. How many elements are there in the first 23 rows? The sum of all of this, which is nothing but 23 into 24 by 2, which is 276, right? So the first 276 elements are already taken by the first 276 elements are taken by the first 23 rows. In the 24th row, we want the 23rd cell, which means to this, again, the 23rd value here is 23rd from here because the indexing always starts from 1. Column numbers also start from 1. So 273 plus 23. This will become 299. Okay. So the 299th element that we store, is from this index in our array. Now, the answer that I wrote for this was 299. One of my teammates corrected me and said, you have missed this aspect. We are going to store it in an array. And we said the array indexing starts from 0. So the 299th number will be stored in index 298. So the answer to this is 298 and not 299. So there are 2 places where people commit mistakes. I have done this, to be honest with you. Okay. It's not 299, it's 298. That's one. People forget that in a lower triangular matrix, if you want to store it optimally, you don't have to store all of these. That's the second part that you have to be careful about. If you're careful with these 2, and if you're careful with the fact that the matrix indexing is 1, 1 and the array indexing is 0, these are 2 aspects that you can't mess up with. Again, we have intentionally made it slightly tricky so that there are more places where students would make silly mistakes. Okay, so the right answer here is 298. Okay, that's how it works. Again, some of you got it. It's easy to understand that and easy to get it. Again, sorry that we have overshot by a few minutes. We wanted to close it out in about 60 minutes in the interest of everyone's time. Unfortunately, we could not finish. I overshot by a few minutes. Again, from the next session, we will start at sharp whatever the time we announce. So let's assume we announce at 7. We will start at sharp 7 so that there are no delays. Any questions that we cannot. Again, the objective here is to solve problems, right? So anything that we could not answer, please feel free to go to gate.appliedcourse.com. Here is our email address. Please email us. Anything that you think we have a correction in our examples or problems, please email us. If there is an error that we made, we will correct ourselves. If there is no error, but there is a confusion from your side, we'll try to respond back to as many emails as possible, as fast as possible. Okay, sounds good, folks. Thank you very much. Thank you for joining in. And sorry, apologies for those people who wanted to leave within 60 minutes. We'll try to close it out in 60 minutes sharp. Thank you very much.